Hello students, and welcome to this lesson on exponential functions. Our objective today is that we will analyze exponential functions and determine their applications using journal notes and practice problems. Now, before we can start analyzing, we have to define them, right? An exponential function is any function which has its variable in the exponent. And the simplest version of this is going to be our parent function, which we're going to call f of x is equal to a times b of x, where a is a real number and where b is also a real number. All right, so let's go ahead and analyze a basic version of this to see kind of what is going to go on here. So generally, our exponential functions will take one of two shapes. So either it will be exponentially growing or it'll be exponentially decaying, and that will kind of determine what the shape is. Now, regardless of whether or not it is exponentially growing or exponentially decaying, they're going to share some properties. So one of the properties is that the y-intercept here is always going to be 0, a. And then the purple here, or the decay, is going to be such that b is less than 1, but still greater than 0. So that will be a decay situation where 0, well, b is pretty much a fraction less than 1. And then when we're growing, it's going to be b is greater than 1. So those are our two main situations. One thing that they'll always share is that the y-intercept is always going to be 0, a. So whatever a is, that'll be your y-intercept. And then a lot of the times, they're both going to have the same asymptote. So it doesn't matter whether it's growth or decay, their asymptote will be the same regardless. And we'll learn how the asymptote is controlled when we get to transformations. But just know that in our standard version of this, we have y equals 0. So in the parent function, our asymptote is y is equal to 0 in most cases. Now you see they kind of approach their asymptote in a little bit of a different way, but we'll get into that more as we see the difference between growth and decay. All right, so now that we know some of the attributes of exponential functions, let's go ahead and see if we can do some math with them. All right, so I want to compare two different exponential functions. So I have the function 2 to the x and 10 to the x. So I'm just going to go ahead and make a little chart down here. I have my x and I have my f of x, and we're just going to use the numbers -1, 0, 1, and 2, and then same thing over here. So we're going to say, go ahead and take this and make another version of it over here. All right, so let's go ahead and plug these in and see what we get. All right, so for this first function, I'm going to plug in 2 to the x, so 2 to the -1 power. So now we're encountering something where you're talking about a negative power. So we have 2 to the -1, then I have 2 to the 0, 2 to the 1, and 2 to the 2. And my outputs, or my y values here, are going to be, now we have this weird negative power, right? So really what we're saying is 2 to the -1 is going to be 1/2. So my output is going to be 1/2. So we see how that happened there. That negative flips, it gives me the reciprocal of my original number, and then we take the power of that. Then we have 2 to the 0, which is going to be 1, 2 to the 1, which will be 2, and 2 to the 2, which will be 4. So now we have some nice points to graph. We have -1, 1/2, so -1, 1/2 here. Then we have 0, 1, we have 1 comma 2, and we have 2 comma 4. And if we go to 3, right, we know that 2 to the 3 is 8. So 1, 2, 3, 4, 5, 6, 7, 8. So we have a nice point there. And then if I say 2 to the negative 2 power, right, that's 1/2 times 1/2, so that gives me 1/4. So what we see is we've got this nice curve that's developed here. All right, so that's 2 to the x power. Then over here we can do the same thing. So over here we're going to see 10 to the negative 1 power, 10 to the 0, 10 to the first, and 10 to the second. And our outputs will be 1 over 10, 1, 10, and 100. So we see how this is actually going to grow much faster. So we have 1/10 already right here. We have already 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 up here. We have 1. So the difference between these appears that something that has a base of 10 is going to grow much, much faster than something that has a base of 2. So that's going to be the main difference in our changing of the base. So let's go ahead and list out some of the attributes here. So we have A is equal to 1, B is equal to 2. Then we have our y-intercept is at 0, 1. And then our asymptote is going to be y equals 0. Then over here we have A is equal to, again, 1, B is equal to 10, our y-intercept is at 0, 1, and then our asymptote is at y equals 0. So these functions really are not all that different, and what we'll see is that these are two of the more similar functions that you can have. The main difference is their growth rate. All right, so now let's look at the difference between growth and decay. So we've already seen a little example of exponential growth, right, and exponential decay. So let's go ahead and do this in a more algebraic way. So let's say that I have 2 to the x as my function, and over here I have 1/2 to the x. So I'm choosing these because they're kind of related, right? We have 2 and we have 1/2. And what we'll see is that they have similar shapes, but they go in different directions, right? We can talk about increasing and decreasing. A growth function is going to increase in the positive direction. A decay function is going to increase in the negative direction. So let's go ahead and make some charts. So we're going to give them the same inputs. So we have x, we have y, we have x, and we have y. All right, so we're going to choose -2, -1, 0, 1, and 2. And then from there, what we'll see is that we can choose the same inputs over here. So -2, -1, 0, 1, and 2. And if we plug these in, we see that we have 1/2 to the -2 power. Well, that'll give me 4. 1/2 to the -1 power, that'll give me 2. Then we have 1. Then we have 1/2. And then we have 1/4. Then for 2 to the x, this becomes 1/4. This will be 1/2. This will be 1. This will be 2. And this will be 4. So if I take an interval, say on the x interval, -2 to 1, and I want to know what the minimum and maximum are there, then my y values will become such. So I would say my minimum value here is 1 over 4, and my maximum value is going to be 4. Sorry, 2. And if we were to ask the same question over here, I want to know the maximums for the x values, -2 to 1. So I'm asking the same question again. My outputs, my y values, well, now my minimum comes from right here, 1/2, and my maximum will come from the -2, so that'll be 4. So we see how these are going to be slightly different, right? They have different intervals, and it's because they are kind of mirror images of each other across this, this y-axis. All right, so your reflection today is what situations might be modeled by exponential growth? What about exponential decay? Think about maybe applications in science that you've seen, right? You might know a little bit about the exponential function already from biology. So go ahead and go through, take some time to think about that. Write your reflection. When you're done with the reflection, let me know so that I can sign off on it. And then your assignment for today, along with your homework, is going to be numbers 1 through 13 on 7-1. So go ahead and do numbers 1 through 13 on 7-1. All right, have a wonderful day, and let me know if you have any questions. Goodbye.